So good afternoon.
Good
Okay,
afternoon, sir.
thank you. So welcome back. This afternoon we want to look at a very interesting topic. This topic is called STP. STP is a very important protocol that you will be configuring as young network engineers in order to prevent loops on your layer 2 devices. So in this particular chapter, we want to understand how these loops can occur, what are the problems they can cause, and therefore how STP works in order to prevent them from occurring. So STP principles and configurations. The forward. So on an Ethernet switching network, we have redundant links which are used to implement link backup and enhance network reliability. However, the use of redundant links may produce loops, leading to broadcast storms. That is the first problem of loops. Number two, unstable MAC address table. So we need to understand how loops do those two. As a result, communication on the network may deteriorate or even be interrupted. So to prevent loops, IEEE developed a protocol called STP. Devices running STP exchange what we call this one, BPDUs, Bridge Protocol Data Units, to discover loops on the network and block. So how it works, by the way, is this: block appropriate ports. So in summary, STP blocks some ports in order to prevent loops from occurring on your network. So this enables a ring topology to be trimmed into a loop-free tree topology. So it creates a tree topology, preventing infinite looping of packets and ensuring packet processing capabilities of devices. So IEEE introduced the rapid spanning tree to improve the network convergence speed. As you're going to learn, STP takes quite some time before it converges. Convergence means the time it takes for it to set up and be able to start working, and therefore data can be forwarded. So that's what we're calling the convergence speed. So RSTP is rapid spanning tree, which was the improvement of STP. So we're also going to look a bit into RSTP. So by the end of this chapter, you should be able to... Okay. Dennis, you can read for us? Okay. So by the end of this chapter, you should be able to describe causes and problems of layer 2 loops. Then basic concept and working mechanisms of STP. Then how different is STP from RSTP? Then we do some configuration, STP configuration. Then we also look at other methods that can be used to remove loops from our networks while still ensuring that we have redundancy in order to improve network reliability. So let's begin with an overview of STP. STP in full is spanning tree protocol. Main function to eliminate loops. Layer 2 loops. By the way, in networking, loops can be categorized as either layer 2 loops or layer 3 loops. So layer 3 protocols have a way of ensuring that you don't have loops at layer 3. But STP particularly was created to eliminate layer 2 loops. Layer 2. Let me just call it that. Layer 2. Layer 2 loops. So it will work among that. So the background of this is this. In a simple network, sometimes we might not. Yes. Oh, how layer 3 eliminate loops? I don't think you can be asked about that, but I think we've seen one way in which layer 3 devices eliminate loops. Dennis, kindly check on your machine. I think there's a sound it's making. I don't know whether it's on your end or mine, but there's a beep that keeps on recurring. Maybe check on that. Okay, who can remind us? When we were looking at the IP header, we looked at one field and we said that field is used to ensure that packets cannot loop forever on the network or the internet. Which field is that on the IP header? Yeah? Anthony? The TTL, right? Very good, the TTL. So that's one way in which layer 2 loops are prevented. Otherwise, other than the TTL, you get some protocols like BGP have ways of ensuring that we don't have layer 3 loops. Also OSPF, I think. If you learn more about OSPF, especially when you're talking about multi-area, you remember when you talked about OSPF multi-area? So there are strategies that are used to ensure that we can't have data looping between the areas. Yeah. Okay, so if you check my videos on HCIP on OSPF multi-area, you're going to understand how. Is it my mic that keeps shifting and disconnecting, or what? What is that sound? Let me just check that out. Okay. So let's proceed. As I was saying, uh, these this particular design here is a design without redundancy. Without redundancy. In computer networking, when we talk about redundancy, we mean that you're providing more than one way of accessing the network. So you have more than one option. So in this particular simple topology, we don't have that. Normally, when you talk of redundancy, you can have device redundancy, where, for example, on aggregation layer, you have more than one switch. So that's called device redundancy. Another common form of redundancy is link redundancy. But on this particular example, we don't have any of those. We don't have any of those. So really, what happens here is that if this device fails, this one here, then everyone else in the network is isolated. They can't be able to access the internet. Similarly, if this link fails, then people will also be isolated. So that's the problem of not having redundant devices or redundant links. So they introduce a problem we call single point of failure. Single point of failure. Failure. Also called like that in short. Single point of failure. So that's the main problem of not having redundancy. Now, this one, for example, is one that has redundancy. So we have device redundancy. So on the aggregation layer, we have two switches. We have these two switches on the aggregation layer. Okay. So for that matter, the access switch can access the internet via that aggregation switch, or it can access it via this aggregation switch. So we've provided that redundancy, and for that reason, we can easily have a loop here. Because if a broadcast packet is sent to this guy will send it out like that, and also like this. When this guy receives it, they're going to send it like that, but also like this. So you can see that we already have a loop. Here. So you can have a loop. So that's how a loop can occur. Now, as we know, if we have a loop, these frames are going to increase with time. They are going to consume all your bandwidth and CPU resources or switch resources, and your network is going to shut down. It's going to fail. So that's why we don't want loops in our networks. Okay, so layer 2 loops can also be caused by human errors as a network administrator. For example, if you create a connection between these access switches here, then you have a loop. So incorrect operations, for example, connections of cables between devices are incorrect. So you're not supposed to do this, especially on the access layer. Then number 2, we also have incorrect manual configuration. It is okay for you to have two links that are interconnecting the access layer switch and the aggregation layer switch, so that one can act as a backup. But in order for you to achieve that, you need to use a method that we are going to learn later called link aggregation. So link aggregation is binding links, physical links together, so that they can work as a single logical link. So that's what we call link aggregation. Otherwise, if you fail to aggregate them, then you're going to have a loop. You're going to have a loop here, because broadcast is sent, it's going to be sent out to via that interface too. So you already have a loop. You already have a loop there. So those are instances where you can cause a loop as a network admin. Okay. So the issues caused by loops on a network, as we said, the first problem of loops is broadcast storms. Then the other one is MAC address flapping. So you need to understand these two problems and how they occur. So first of all, broadcast storms. Let's look at number one. Switch 3 receives a broadcast packet, right? So it's going to send it out like that and also send it out like that. Are we together? If switch 2 receives that packet, what will happen? It's going to send it out through this interface, right? So that's number 3 here, like that. Now, let's follow up with this. If this gets here to switch 1, what happens? Switch 1 is going to forward it how? Like this, right? Are you seeing it has already come back to the switch where it originated from? So we are having a loop. Similarly, if we follow the other path, send it here, then this guy will send it here. Then this guy receives the broadcast packet from switch 1, he will send it here. So you're having a loop already. So that is what we call a broadcast storm. A broadcast storm. So as we've said, if we have a broadcast storm, your bandwidth is going to be consumed, your switch resources is going to be consumed, and your switch performance is going to deteriorate rapidly and even interrupt the service by maybe restarting. Now, the other issue with loops is causing what we call MAC address flapping. So let's try and understand how this happens. So with MAC address flapping, this guy receives switch 3 receives a frame whose source address is this 788A. Now, when this guy receives that, it updates in its own MAC address table that, hey, I have connected this particular MAC address I have learned that MAC address via maybe G001. Are we together? Or let me just use this example that is using S1. Okay, so this is what happens. This comes here. The source address is that. Then it is sent to switch 1. So switch 1 is going to update its MAC address table. But hey, I have learned, remember this is a broadcast frame. I have learned this MAC address via which interface? G001. Are we together? But after a short while, it's also going to receive the same frame because it's a broadcast. It's going to receive the same frame from switch 2. And therefore, it's again going to update its MAC address table and change it from G001 to G002. Because, see, the source MAC address of that frame will still be the same. Are we together? So it's gonna change it. So that is what we call MAC address flapping. MAC address flapping. So that's the problem. That's the problem that is caused by having loops on our network. Okay. Dennis, you have a question?
No, I just have a problem with connection.
Oh, okay, sawa. Kindly mute your mic. Okay, thank you. So, STP, introduction to STP. As we've said, STP in full is spanning tree protocol. STP is used to eliminate loops on the switching network. Why is it that we don't want problems with loops? As we've said, problems with loops Number one, we have said broadcast storms. Number two, we have said MAC address flopping. Number three is what we call duplicate data frames. Duplicate data frames. See, when I was explaining MAC address flapping, did you see that switch 1 is receiving the same frame from two switches? Huh? So see, we are receiving the same frame, duplicate frames. Yeah, so that's what we call duplicate data frames. Okay. So what STP does, is number one, to detect loops. Number two, block redundant links. Number three, also detect topology changes. So we are going to see how it does that, and really it does this by creating a loop-free tree network. It creates a loop-free tree network. Okay, so in this example, when STP is deployed on the network, the switches are going to exchange STP BPDUs and calculate the tree topology. Finally, one or more ports on the network are going to be what? Blocked in order to eliminate the loops. So we have already seen that when we have a connection like this and we receive a broadcast, we're going to have a loop. So in order to avoid having that loop, we might need to block a certain port. In this case, this one, so that we don't have a loop anymore. So that is what we are having here. So we are going to understand how that is done and why this switch is called a root and how this port is blocked. So when we say that we have a tree topology, then this is what we mean. From a ring topology, this one is ring, to a tree. So we can't have, we're having a tree, so we can't have a loop. So regardless of the number of switches we have, still going to create a loop. Do we have, if you're in year 3, most likely you've learned about data structures. There's a unit called data structures, right? Most likely. So the math behind how to create the tree, most likely you learn it in that unit. Okay. So as I said, STP can be able to detect topology changes in order to dynamically respond and adjust blocked ports. So in short, what you're saying is we've blocked this port, but what if this interface here goes down? Or what if this interface here goes down? Because if let me undo that. If this interface goes down, we can still then be able to access this via that. So it means we have to enable this blocked port. So in this particular example, we're just being shown that if this port goes down, if this link here goes down, then this one is reactivated. This one is restored. This one that had been blocked, so that we can still be able to access switch 1 now via switch 2. So other than blocking ports, you're going to understand how Then we are able to monitor the topology change and be able to reconfigure the ports. Oh, so as I said earlier, loops can be categorized as layer 3 or layer 2. Layer 2. And I think we have already discussed about that. So layer 3 loops are called routing loops. Most dynamic routing protocols have a way of preventing these particular loops, but you can also use the TTL field to do that. Okay. So layer 2 loops are caused by redundancy when you do redundancy on your network, or when you do incorrect connection between your devices, like you don't bundle up the links. So the protocol that is used to do that is STP. So where do we apply STP on a campus network? We deploy STP on these switches. So between the access switches and the aggregation switches, because that's where we provide redundancy, and therefore there is a probability that a loop may occur. So normally we configure STP there. Is that clear? So let's have a look, an overview of STP. So they're used to prevent loops on a local area network. Devices that run this will exchange TCP information, what we call STP BPDUs, Bridge Protocol Data Unit, to discover loops on the network and block certain ports in order to eliminate the loops. After running on a network, STP will continue to monitor the network status in case the network topology changes. By network topology change, it means either a link has gone down or a device has gone down. So how then do we respond to that so that we can still have network communication? So STP can detect change and automatically respond to this change. So in this way, the network status can adapt to the new topology, ensuring network reliability. So we are going to see how. With the growth of the LANs, STP has become an important protocol for the local area network. So that's why it's important that you understand how it works. Basic concepts and working mechanisms of STP. So just as an introduction here, in STP, we will be referring to a switch as a bridge. Is that clear? Every switch has a unique identifier. That unique identifier is called a bridge ID or BID. Now, the BID is made up of two parts. Number one is a 16-bit bridge priority. Number two is a 48-bit MAC address. The bridge priority is configurable, meaning you can be able to change it. It ranges from 0 to 65535. However, when you're configuring the bridge priority, you must configure it with multiples of 4096. So later on, we are going to see how the bridge ID is used. The bridge ID is used to create, to elect what we call the bridge, the root bridge, But just hold on that idea for now. We are going to see how that is really implemented. Okay, so let's look at this particular example. So in this particular example, this is the bridge ID. This is the bridge ID. The first part here, before the dot, is the bridge priority, 4096. Then this part is the MAC address of that particular switch. The MAC address of that particular switch. So that is what we are seeing here. Okay. So the root bridge. The root bridge, in summary, will be the root bridge will be the center of the tree. So you've said STP forms a tree topology. So the very center of the tree at the very top, that is where we have the root bridge. So the root bridge is the root of the STP network. So after STP starts to work, what does it do? It elects the root bridge. So root bridge is key for topology calculation of the spanning tree, and it is the root of that particular tree. The device with the smallest BID, bridge identifier, is elected as what? Is elected as the root bridge. Now normally the root bridge at the beginning, the switches are going to compare their BIDs. So the one with a smaller value of the BID is going to be elected as the root bridge. Now, normally how this happens is that it first compares the bridge priorities. Are we together? It first compares how the election of the root bridge works. It first compares the bridge priorities. In this particular case, the bridge priorities are the same, right? So if the bridge priorities are the same, then they go ahead and compare the MAC address. So whoever has a smaller MAC address becomes the root bridge. As you can see, all these MAC addresses are the same other than the last bit. So this one is A, this one is B, this one is C. The other parts are just the same. So that's why, because this one is the smallest, this one, switch 1 here, will be elected as the root bridge. Are we together? Yeah, so don't forget that election rule. Okay. The other important concept in STP, yes. Exactly. So what she's asking is if the bridge priority here is 4096, then the bridge priority here, what is 4096 times 2? It's supposed to be? We can say 4100 times 2 is? 4100 times 2 is 8200, Then we subtract 8. 8192. 8192, like that. So if that has 8192, and in fact, this one can even have 0, a bridge priority of 0. So if this is the case, then this guy will be elected. this guy will be elected as the root. So whoever has a small priority. So at first, it compares the priority, just the priority. If the priorities are the same, then it compares the MAC addresses. Okay. So the other important concept in STP is the concept of the cost. Now, the cost is important because it's used to create what we call the root path cost. The root path cost, or RPC. RPC, on the other hand, is used to determine the role that the port will play. So we are going to look at RPC shortly, but just know that every interface is associated with a certain cost. Most of the time, of course, this cost is closely related to the port bandwidth. So normally, if you have a higher port bandwidth, your cost is going to be smaller. However, on STP, you can also run a command in order to manually configure the cost of a port. For example, you want to advantage it or you want to disadvantage it. So you can manually configure. So we're going to see that, how to do that at the end of this chapter. Okay, so these are some of the cost calculation methods. Normally, we have three standards that can be used for this. So we have that one, IEEE 802.1d. Then we have 802.1t. Then we have a Huawei legacy standard. So you can choose either of these to use in the calculation. So just as an example, a 1 gig link that is working on full duplex mode. Have we ever talked about duplex modes? We've never. Oh, sorry. Okay. Duplex modes. We have two duplex modes in data communication. The first one is called full duplex, and the second one is called half duplex. The duplex mode determines whether data can be able to be sent and received simultaneously on a link. Whether we can be able to send and receive simultaneously. An example that I keep giving of half duplex is the over. You know over. We call them over huko kwetu Shago, because when one person talks, they have to say over and release the channel so that the other person can talk. So half duplex is when you can send and receive data, but one at a time. Are you getting the point? Then you can think of your mobile phones. The mobile phones we are using to communicate today, they are operating on full duplex, because you can send and receive at the same time. Most of the time, for example, when it comes to this full duplex, we use different channels or different wires to send and receive. So for example, on an Ethernet cable, if we have 8 wires, then maybe 4 are dedicated to sending while 4 are dedicated to receiving. Are you together? Yeah, so that's the main difference between full duplex and half duplex, being able to send and receive simultaneously. Okay, so as an example, if we have a 1 gig link that is transmitting at full duplex, if we are using this standard, the cost for that link is going to be 4. Are we together? On the other hand, if it's 100 Mbps, the cost of that link, if it's full duplex, is going to be 18. Yeah, so as we said earlier, if the cost is lower, then we we prefer that one, okay? We prefer that port. Are we together? Yeah, so we're going to see how. Now, the other thing I need to mention here is that by default, Huawei devices uses this standard, if I'm not wrong. Okay. Okay, so RPC is what we call root path cost. RPC is root path cost. Now, RPC is the cost from a switch port to the root bridge. The cost from the root port to the switch port to the root bridge. It is important. RPC is important when we are doing STP topology calculation. So we are going to see how. So RPC from a port to the root bridge is the sum of all inbound ports along the path from the root bridge to that particular device. So what do we mean? What do we mean when we say that? So in this particular example, S1 or switch 1 is the root bridge. So we want to calculate the RPC of this particular interface here. So the RPC of that interface is going to be the cost of all inbound interfaces. So the first inbound interface we have is this one. The cost of this inbound interface is 500. So we write 500. Then the other inbound interface is this one. This one. The cost of this interface is 2000. Therefore, we add 500 plus 2000. So the RPC of this port is 2005. Is it 2000 or 20? 20,000, eh? 20,500, okay? Yeah, so that's how we add the RPC. So the RPC is important in selecting what we call the root port. So we're going to see how in just a short while. Okay, so we also have what we call the port ID. Port ID is easy. The port ID is made up of two parts. The first part is called the port priority. Then the second part is the port number. The port priority, by default, it's 128 on Huawei switches, but you can run a command to change the port priority of a particular port or interface. This particular port priority, we are saying, okay, let me begin from here. We are saying that port identifier, PID, PID, is made up of port priority plus port number, the port number. So the port priority can range from 0 to 240. But when you're configuring it, you configure it with multiples of 16. The port number, for example, if you have a port whose number is Z002, then the port number is 2. So the PID for such a port if the priority is 16 and the port number is that, then the PID will be 16.2. Are we together? So that's what we're having here. So this particular port is port number 24. The priority is the default 128. This one here is port number 21. Priority is the default priority 128. And so on and so forth. Okay. Then we have BPDU. BPDU. So BPDU is Bridge Protocol Data Unit. Bridge Protocol Data Unit. BPDU. So just like we saw in OSPF, we learned about different packets that are used to make OSPF work. So for STP, that packet is called a BPDU, a Bridge Protocol Data Unit. So normally switches will exchange information and any parameters they need by using the BPDU. So that is what we are saying here. Now we have two types of BPDUs. The first one is called a configuration BPDU, and the second one is called a TCN BPDU, or topology change notification BPDU. So for the configuration BPDU, this is what we will be receiving from the root port all the time. So the root port will be proactively be sending down the root port, you see. So in this example, this one is the root port. So it's going to be sending down the tree configuration BPDUs. It's going to be sending configuration BPDUs. Otherwise, also when the TCP is initializing, the other switches will also send configuration BPDUs. Are you getting the point? We exchange BPDUs in order to carry out an election, for example. Otherwise, this one, topology change notification, we only send a TCN when we have a topology change, link failure or device failure. So these are the fields of a BPDU. These are the fields of a BPDU. So the first one is the PID. Normally it has the value 0, PVI 0. BPDU type. So BPDU type can either be a configuration BPDU, it will have that value, or a TCN BPDU, it will have that value. Flags. So for STP, it uses only the leftmost 2 bits and the rightmost 2 bits. So these 2 bits are used to identify what we call a topology change acknowledgement, TCA, or a topology change. So we are going to look at that in a short while. Then we have the root ID, which gives the BID of the root bridge. So if you want to know who is the root bridge, you look at the value that is on this field. RPC is used to store the cost of the path from the current port to the root bridge. So you've seen how to add RPC. Bridge ID is the BID of the sender. So whoever has generated this particular BPDU, their bridge ID will be saved there. Port ID, port that sends this BPDU, which consists of the port priority and port number. So you've seen the port ID. It contains the port priority and port number. So the interface through which we sent this BPDU, its details will be found here. Then you have the message age, the maximum age, the hello time, and the forward delay. So you need to understand these three. Please concentrate. Concentrate. You need to understand these three, very important. Expect a question on these ones. So message age is the number of seconds after a BPDU is sent from the root bridge. the number of seconds, meaning the value will increase by 1 each time the BPDU passes through a network bridge. So it refers to the number of hops to the root bridge. So when a BPDU is sent downstream to the tree, it will have at the root it will have the value 0 message age. When it passes through one switch, 1, incremented by 1 again. When it goes to another switch, 1 1 1, like that. So that is what we call the maximum age, incremented every time the BPDU passes through a switch. Then we have the maximum age. So if the bridge does not, if a bridge or a switch does not receive any BPDU for a period of time, the lifetime of the network bridge reaches the maximum. So the network bridge considers that the link connected to the port is faulty. The default value for this is 20 seconds. So that means that if in 20 seconds I don't receive a BPDU from the upstream switches, then I conclude that there is a problem with the root bridge. So that is what the maximum age does. So normally it counts down. It counts down 20, 19, like that, until it gets to 0. If it gets to 0, it generates what we call a topology change notification, a TCN. Otherwise, we also have the hello time. Hello time is the interval at which the root bridge sends BPDUs. By default, every 2 seconds, the root bridge will send BPDUs saying, hey, I am the root. Hey, I am the root. Hey, I am the root. Then lastly, we have the forward delay. We are going to learn about the learning state and the listening state. So the time that is spent when transitioning from listening to learning is what we call the forward delay. And normally the forwarding, by default, the forward delay is how many seconds? 15 seconds. So those are the fields. Those are the fields of a BPDU. Now, these particular fields on the BPDU are the ones that are used. The root identifier, root path cost, bridge, and port identifier are the main fields of the configuration BPDU. So STP selects the optimal configuration BPDU in the following sequence. So normally it compares what? 1 with the smallest, bridge, ID. Otherwise, it goes and looks at who has the smallest, RPC. Otherwise, it looks at who has the smallest, BID of the network bridge. Otherwise, it looks at the port identifier. So among the 4 rules, each rule corresponds to a field in the configuration BPDU, as you've seen here. So the first rule is used to elect the root bridge. So we're going to look at each one of them individually. So the first one, which is smallest BID, is used to elect the root bridge on the network. Following rules are used to elect the root port and designated port. So we are going to see what is a root port and what is a designated port and what is what we call an alternate port. Okay. So configuration BPDU forwarding process. At the very beginning, what happens? At the very beginning, every switch sends out a configuration BPDU. When you send out the configuration BPDU at the beginning, you assume yourself as the root bridge, and therefore on the BID you enter your MAC address saying that, hey, oh, not the MAC address really, but the bridge ID. you enter your bridge ID saying that, hey, I am the root. It's like saying I'm the president. So everyone announces themselves as the president. So initially that is what happens. Otherwise, normally the path cost from the root is 0, right? Yeah, because you've not added anything. There's no inbound. You've not added any cost. So anytime you're assuming yourself to be the root, the path cost is going to be 0. Then the bridge ID of the network bridge, of course, is your own. It's the bridge ID of the switch that has generated this configuration BPDU. Then the PID, you can see that the PID value is the PID value of this particular interface. So switch 2 then will receive this configuration BPDU. Then it will compare the bridge ID. Do I have a better bridge ID? If what I've received is the better bridge ID, then I don't change this. Then of course I will add the path cost. So the cost for this interface is 2,000. So 0 plus 20,000, sorry. 20, like that. Then after that, you enter the BID of the network bridge. How to do that? To enter the BID of the network bridge. So now you replace it with your own bridge ID there, because you are the one who is resending this configuration BPDU. And then of course you also enter your PID, the interface through which we are sending this configuration BPDU. Are we together? Yeah. So I hope that is clear. And just to mention here, let's assume that, for example, this guy, switch 1, is the root. So normally what happens, switch 1 will send a configuration BPDU just to announce that, hey, I am still the president. So how does it get to the other downstream switches? But let me just, I've used that term and I think I need to explain it. Where am I going to draw this? Okay. I can't. Dennis, can you hear me? I'm not the host. So sorry. Dennis, please. I'm not the host.
I'm hearing you.
Okay, please mute your mic.
I have a problem today. I'm on and off network. It's raining heavily.
Oh, sorry about that. Sorry. Okay. So sorry about that. Okay. So okay. So if we're having an arrangement like this, so if it builds a tree like this one, so this is what you're calling a tree. So you can't have a loop, right? When you have such a tree, you can't have a loop, right? Yeah. So this is what you call the root bridge, right? Root bridge. Then these other ones are called non-root bridge. So when I talk of downstream switches, I'm talking of this because packets will be moving downwards like that. BPDUs will be moving downwards. So they are called downstream switches. Otherwise, when we send a TCN, topology change notification BPDU, the topology change notification will be going upstream. Are we together? So downstream, upstream. Are you getting the point? The difference between upstream and downstream? Yeah, so that's what I mean when I keep on mentioning upstream and downstream. So, as I was saying earlier, you have a question, Kellen? Oh, you don't understand the root path cost? the RPC, the root path cost from the root is 0. Oh, let me then use this. So here, sorry. So here, the root path cost here, RPC here, is 0. Are you together? Because how RPC is calculated is we calculate RPC by adding the cost of all the inbound interfaces. So for example, if this is 500 and this one here is 500, the cost for this interface is 500. The cost for this interface is 500. So the RPC from the root bridge to this bridge here will be, the RPC will be 0 plus 500 plus 500. So it's going to be 1000. So that's how we add RPC. So we don't add the cost of the outbound interface. We don't add the cost of that. We don't add the cost of that. We only inbound interfaces. Sawa. Have I answered your question? Root path cost. Ni kwa interface. So the root path cost is on the interface, right? It's on the interface that we calculate the cost, right? Using one of those costing standards. By default for Huawei devices, 802.1t. Okay, so as I was saying, every time a downstream switch receives a configuration BPDU, it recreates that configuration BPDU before sending it downwards. By recreating it means it changes what? No, it doesn't change the root because the root will remain the same, but it will change the path cost, right? Because it will have to add that. It will also change the BID and the PID, right? Yeah, before sending it down to the downstream switch. Is that clear? Yeah. Normally that process takes about 1 second. You receive a BPDU and then you send it down. And you're sending it down just reminding the guy who's down there that this is still the bridge, okay? Okay, so let's move on to STP calculation. STP calculation. So select a root bridge on the switching network. So as we said, everyone will begin by sending configuration BPDUs declaring that they are. You see, these are configuration BPDUs declaring that, hey, I am the root. I am the root. But as you declare, when you receive a better BPDU, that is one that has a lower value, for example, in this case, the switch 1, then you stop sending on the BID, on the bridge identifier field, you stop sending your own. You now start sending for that one. Are we together? So eventually, everyone will exchange that and know that, this guy has the best. And therefore, this guy is the root. Are we together? Yeah, so that's how it happens. And that is how switch 1 will be elected as the root bridge. So switch with the smallest bridge ID becomes the root bridge. The role of the root bridge can be preempted. Please don't forget this. Most likely you'll be asked this in the exam. Preemption means if we connect another switch that has a better bridge ID than this, then it will trigger an election. It will trigger an election. So the root bridge can be preempted. The root bridge can be preempted. Okay, to ensure the stability of the switching network, you are advised to plan the STP network in advance. and set the bridge priority of the switch that is planned as the root bridge to the minimum value, which is 0. So normally we want maybe the most powerful switch or the switch at the aggregation layer to act as the root bridge. So in order to ensure that it's the one that will be elected as the root bridge, we configure it with a root priority of 0. So automatically, if election occurs, it's the one that is going to be elected. If a new switch is added, the default priority is 32,000 and something. So it still will remain the root bridge. Are we together? Yeah. So that's why we do that. So still part of STP calculation. After electing a root bridge, in this case we've selected S1 as the root bridge. So the non-root bridges will select what we call a root port from its ports. How many ports do we have? They're called port roles. So port roles, we have root port, we have designated port, and we have what we call an alternate port. So these are the three STP port roles. So in this particular at this particular point, we're just looking at how do we select a root port. Now, a few things you're supposed to know about the root port is that a non-root bridge has only one root port. When a non-root bridge switch has multiple ports connected to the network, the root port receives the optimal configuration BPDU. Root port is located on each non-root bridge and has the shortest distance away from the root bridge. So normally, how we select the root port is by using RPC. We use RPC to find the port that has the lowest cost. If you have the lowest cost to the root, then we elect you as the root port. Are we together? Yeah, so that's how we elect a root port. So you can see on switch 3 here, this port has been elected as a root port. On switch 2, this one has been elected as a root port. Does it make sense? Do these two ports really, are they closer to S1 compared to this one and compared to this port? Do they offer the shortest distance away from the root bridge? They do, right? Even just by using your eyes, really. Okay, so the other port is called the designated port. So the designated port I'm sorry. I think there's something I've not said. On root port, there are things I need to discuss that I haven't. Election process. So number one, the switch will first compare RPC. So that is what is used to select. But if the RPC is the same, then the root will compare the bridge ID. BID. If the bridge ID are the same, then they will compare the PID. And that should be able to give us the tiebreaker. So if we have a scenario like this, look, we have another link here. So are you seeing if we compare this interface and this interface? See, they're going to have the same RPC, right? See, they're also going to have the same bridge identifier. Because they're connected to the same switch. See, the bridge ID is going to be the same. But we know that the PID has a port number. Can the port number of these two interfaces be the same? No, right? Yeah, so this then can be used to can be the tiebreaker. So remember, with switches, normally in most protocols that deal with switches, the smallest value has a higher priority. Are we together? Whoever has a smaller value, higher priority. Okay, designated port. Designated port. So after the root port is elected, non-root bridge uses the optimal BPDU received on the port to calculate the configuration BPDU and compares the calculated configuration BPDU with the configuration BPDU received by all ports except the root port. If the former is better, the port is designated. If the latter is better, the port is not a designated port. Then they end up by saying, in most cases, all the ports on a root bridge are designated ports. So in fact, let's just understand that all ports on a root bridge are designated. So in this case, S1 is our root bridge, switch 1. So all the ports will be designated, D for designated. In summary, you can think of designated ports as ports that are used to forward BPDUs to downstream switches. So you've seen the tree. So these ports that are used to send BPDUs to downstream switches are the ones that we call designated ports. While these ports that are used to receive BPDUs from upstream switches are what we call the root port. Are you seeing that? Does it make sense? Exactly. Okay. So how do we elect? The election process of designated. So again, compare RPC. Number 2, compare, if they're the same, compare what? BIDs. If the BID are the same, then we go and compare what? The port identifiers. So that's how we elect a designated port. Okay. So the last port is what we call the alternate port. The last port role for STP is called the alternate port. Alternate port is also called a non-designated port. Alternate port or non-designated port. Alternate. This is a port that is neither a root, that is neither a root or designated port. So we block this port to eliminate loops on a switching network. on a switching network, we simply block this port. So far, the only port in this example that has not received a role is this one. So we block it. We block it. We block it. Now, blocked ports. Blocked ports. Blocked ports cannot forward data. They also cannot learn MAC address. Remember the problem of MAC address flapping? MAC address table flapping? Yeah, so we can't have it. Because if we block a port, it can't learn MAC address. But can receive and process BPDUs. Also, of course, blocked ports can be reactivated. It can be reactivated in case of topology change. In case we have a topology change, we can reactivate it. So I hope that is clear. On the other hand, root port, root and designated can forward data, can learn MAC addresses. They also receive and process BPDUs. Are we together? From the explanation we've given so far of the three interfaces, we've said that on the root all interfaces are designated, right? On the downstream switches, how many root ports can we have on an individual switch? From your understanding of what we've discussed so far, how many root ports can we have on a switch? One, right? Yeah, one and only one. How many designated ports? Yes. How many designated ports can we have on non-root bridges? Non-root bridges, how many designated ports can we have? How many? One, right? Because we are forming a tree. Okay, so I hope you remember that. Okay, so can I give you this quiz? Do I demonstrate this one? And then maybe you try the next one. Is that okay? So we want to identify two things: the root bridge and port roles. In fact, just from looking at it, which switch here is the root bridge? Which one will be elected as the root? Switch 1. Reason being, it has the smallest bridge ID, BID, okay? It has the smallest bridge ID. Then which port? Okay. Then let's discuss about the port roles. If this is a root, so we've agreed that this guy is the root. So root. Okay. So on the root, what will be the port roles on the root for G000? Right? And here, it will be designated, right? We've said all ports of the root bridge are designated. Okay. On switch 2, G001, what will be the port role? The root, right? Ah, good. Why do you think that will be the root? Okay, on G001, G001 on switch 3, what will be the port role? Root, right? Because they offer the shortest distance to the root bridge. Very well. Okay, so of course there's a port we need to block here, and to do that we need to select which port among these two, G002 on S2 and S3, which one is going to be the alternate and which one is going to be the designated, right? So to find the designated, what did we say? First we compare what? Huh? We compare the RPC, eh? See, the RPC for both interfaces, they are the same. Is that true? The root path cost for this, assuming that all interfaces are, actually not assuming, see, all of them are gigabit Ethernet. So the RPC for both of them are going to be the same, eh? Is that correct? Okay. So then we need to go to the next one. We need to compare what? The BID, right? So which one has a smaller BID between switch 2 and switch 3? Huh? Switch 2, right? So meaning that this interface on switch 2 is going to be the designated, right? And if that is designated, then this is the port that we are going to block. So it's going to be the alternate port. And therefore we are going to block this one so that we don't have a loop. So that's how the switch is able to create a loop-free tree topology. A loop-free tree topology. Okay. So the next quiz, you can discuss this. If you have a problem, you can ask, then I'll be able to help. I want you to at least stand up as you discuss this so that you don't fall asleep. Please, let's stand up. I can see a few of us are sleeping. I totally understand. But let's stand up and discuss this. So let's define who becomes the root bridge, then the port roles. So I'll be walking around to check what you've discussed. So make sure you write for me. Just write it down so that I come and confirm. Okay, okay. So, yes, yes, yes. Elaine, are you there, Elaine?
Yes, teacher, I'm there.
Okay, Elaine, from your end, which one is the root bridge?
Hello?
Which one is the root bridge, Elaine?
Teacher, I'm not getting you very well. My network is quite poor today.
Oh, by the way, I'm very sorry.
So, yeah. Hello? Can
Oh,
you hear me?
yes, we can hear you. It's okay. It's okay. It's okay.
You
Oh,
know, I lost like 10 minutes. Now I'm quite confused. I don't know how to answer.
oh, sorry, sorry, sorry. It's okay. No problem.
Yeah.
No problem. Okay. So let's do this. Let's do this quite fast. Hey, do you all agree that this is the root bridge?
Sorry?
This is the root bridge, right? G000 on S1, port roll, designated, right? This one, designated, right? All ports on the root bridge designated, right? Okay. This port on switch 2, root port, right? Good. This port on switch 3, root port, right? Okay. This port on switch 2, designated. Okay. This port on switch 3, designated. This port on S4, oh, this is the one we are blocking. Why didn't we block this one? What did you compare for you to block this one and not this one? I think the RPC to the root bridge is the same, right? RPC is the same for both of them. No. The root path cost to the root for G001 and G002 on switch 4, they're different. See, they're the same. They're the same, right? Yeah. I'm not saying all. See, we've just begun with comparing the RPC. So you see the RPC, they're the same, right? So what's the next thing we compare? Huh? The bridge protocol identifier. So which one has a better bridge protocol identifier? And which BID are we comparing? Which one and which one? Look here, we are comparing this BID and this BID. Are we together? So because this one is smaller, then this one will be preferred compared to this one. Are we together? And therefore this is what we are going to block so that we don't have a loop. Are we together? Because if we block that, then we no longer have a loop. So this will be our root. G001 on switch 4 will be our root port, and this will be our alternate port. Okay. What else can I mention here? Please, we are going to learn about it, but let me just mention that if this root port fails, then this alternate port is reactivated and now becomes the new root port. If this link fails, G001, then G002 is going to be activated, and it will now become our new root port for switch 4. Are we together? Yeah. By that, are you seeing that the alternate port is the backup to the root port? Are you seeing that? That the alternate port is the backup to the root port. Okay. Okay, so for the interest of time, I'll explain this one. So here, we want to find the root bridge. I think that's easy. Root bridge is going to be switch 1. Port roles designated. So that we don't have a loop here, we don't have a loop, we don't have this loop, we need to block one of this. We need to block one of these ports on switch 2. So how to do that? We say number 1, we compare what? RPC, right? RPC for G001 and G002, same, right? Yeah, same. Then we compare what? BID. BID for G001 and G002, same, right? So you're just comparing the BID of switch 1 for both of them, right? And then next we compare what? We compare the PID, right? So who do you think will have a better PID here? The one with a smaller value, right? So G001, right? So this will be our root ports, right? Then we are going to block this one. So that will be our alternate port. Is that clear? Okay, thank you. Okay, so STP has 5 port states. The first one is disabled. Disabled simply means a port is down. Maybe it has been shut down or it has not been connected. So that's disabled. Then the next one is blocking. Blocking, okay, let me just, there are things we're supposed to know. Send or receive. About every state, we're supposed to know whether it can be able to send or receive data, whether it can be able to send or receive BPDUs. Number 3, whether it can learn MAC addresses. Something like that. Okay. So with blocked port, it cannot send or receive data, it cannot learn MAC addresses, it cannot send BPDUs, but it can listen to BPDUs. It can listen to BPDUs. We've just said that the alternate port, which is normally blocked, it will act as the backup of the root port, right? So it has to listen to BPDUs so that in case the BPDUs, we have a topology change BPDU, then it can participate in the election process. So please remember that blocked port listen to BPDUs. So it cannot send, but it can receive BPDUs. Listening, STP considers a port in listening state, such as the root port or designated. Only those 2 ports can be on listening state. This port is still in the STP calculation process. So in this case, the port can send and receive BPDUs, but it cannot send or receive data, and it cannot learn MAC addresses. So that's what we call listening, because it's still in the calculation process, calculating the tree. Then the next one is learning. So learning, just like listening, it cannot send or receive data, but it cannot send or receive data, but no. In learning state, it listens to service data frames but cannot forward them. So it can receive data frames but cannot forward them. And it also learns MAC addresses. Are we together? Yeah, it learns MAC addresses. So it receives a frame, learns MAC addresses, updates the MAC address table, but it can't forward it. But of course, it can be able to listen and receive BPDUs, receive and send BPDUs. Then in forwarding state, it can do all three. Forwarding state is the only state where the switch or an interface can be able to do all this. Send and receive data, send and receive BPDUs, and learn MAC addresses. So those are the 5 STP port states. You can transition from any port state to another port state depending on what happens to you as a port. So for example, you can transition from disabled to down to blocking, or down to blocking, when we configure STP initially. So then you can transition from blocking to listening when the port is elected as either a root port or a designated port. You can also transition from listening to learning if the forward delay timer expires. Forward delay timer expires. So normally we have a forward delay timer of 15 seconds. So the port is still the root port or designated. So only root port and designated can be in this state, can transition from listening to learning. Then from learning to forwarding, the port is no longer the root port. Oh, sorry. No, this is still number 3. Sorry. This is still number 3. So listening to learning, learning to forwarding, number 3. So there is what we call the forward delay timer, which by default is 15 seconds. Then number 4, we can transition, for example, from forwarding to blocking. Forwarding to blocking. So this is when the port is, for example, is elected as the alternate port. So we can also transition from learning to blocking, or from listening to blocking. So that is what we get here. Then the port can also be disabled, or the link can fail. When that happens, you can transition from any of these states back to the down state. So that is what we are getting from number 5 there. So that is what happens. Okay, so let's see now what we call topology change. Topology change. What happens if the root bridge fails? Switch 1 is our root bridge. What happens when it fails? Switch 1 has failed. What happens? So we are supposed to understand how this happens. Okay. So if switch 1 is faulty, number 1, it will stop sending. It will stop sending BPDUs, right? So switch 2 will wait for the maximum edge timer, which is 20 seconds, to expire. Are you together? So what happens is this. Whenever you receive a BPDU from an upstream switch, you refresh the maximum edge timer. You refresh it back to 20 seconds. Then it starts counting down. 19, 18, 17 starts counting down. If by the time you're getting to 0, you've not received another configuration BPDU, then it means that the root bridge is down. Are you getting the point? Or the link is down. That's why you're not able to receive configuration BPDUs. So that's how the maximum edge timer is used. Okay, so if the maximum edge expires, then switch 2 learns that the upstream device is faulty. Then the non-root bridges will start sending configuration BPDUs to each other in order to elect a new root bridge. So they'll start sending again. You see what switch 2 is doing? Sending configuration BPDU. Hey, I am the root. Switch 3 is also sending, hey, I am the root. So after re-election, port A, is this what they're calling port A of switch 3 transitions to the forwarding state after 2 intervals of the forward delay timer. So that means, see, initially when switch 1 was the root bridge, see, this port had been blocked. It was the alternate port, right? Yeah, so now we have to enable it. We have to enable it so that we can be able to do the recalculation. And it will transit to the forwarding state only after 2 intervals of the forward delay timer. And the forward delay timer is what? 15 seconds by default. So 2 times 15, we get 30 seconds. Right together? So are you seeing that we've taken 20 seconds before we finally conclude that there is a fault? It can be a link fault or the root bridge fault, right? 20 seconds, right? Then to change the alternate port from alternate will be on blocking state. To change it from blocking state to forwarding state, again it takes how many seconds? 50 seconds. So normally, when the root bridge fails, the STP network will take about 50 seconds, roughly 50 seconds, maximum of 50 seconds. Maximum of 50 seconds in order to recover. In today's network, that time is unacceptable. You can't have a network being down for 50 seconds. Unacceptable. Unacceptable. So don't forget that the convergence time when the root bridge of an STP fails is roughly 50 seconds. That is the maximum edge timer plus the twice value of the forward delay timer. Okay. So let's look at another scenario. What happens when a direct link fails? What happens when a direct link fails? Okay. So we saw this in quiz number 3. If we have switch 1 and switch 2, switch 1 is the root bridge, and we have 2 links connecting switch 1 and switch 2, then we have to block one. We block one, and we let the other one be the root port, right? So that's the scenario we are having here. So in case this link goes down, switch 2 is going to, on a stable network, when switch 2 detects that the link of the root port is faulty, it will detect because this link is directly connected to it. So the alternate port of switch 2 will enter the forwarding state. After what? After twice the value of the forward delay timer, which is how many seconds? 15 seconds. So for this particular scenario, if a direct link fails, the alternate port restores to the forwarding state after how many seconds? After 30 seconds. So that's the convergence time. That's the convergence time of a direct link failure. Okay. Let's look at indirect link failure. Okay. Sawa. Okay, so here, when the indirect link fails, the alternate port of S3 restores to the forwarding state. So it takes about 50 seconds to recover from an indirect link failure. Okay, so let me try and explain this one. Switch 1 is our root, and therefore this is our root port, this is our designated port on switch 2. We've blocked this port on S3. So if this link fails, this guy is going to wait for 20 seconds for the maximum age to expire before concluding that I have lost the root. So after that, it's going to start to send configuration BPDUs. So it will send configuration BPDUs to S3. S3, when switch 3 receives that configuration BPDU, it's going to transition this alternate port and make it a root port. So it's going to transition from blocking state to forwarding state so that it can be able to forward configuration BPDUs to switch 2. So again, that will take 50 seconds because there's the maximum age expiration, 20 seconds. Then there's the transition from alternate to this forwarding state, which also takes a maximum of 30 seconds. So it takes about 50 seconds for that to recover. Okay. So another problem caused by topology changes can be what we call the MAC address table. MAC address table can be incorrect because of the topology changes. So let's see how this happens. Okay. So this is the MAC address table. So this MAC address table is for switch. Let me see. This MAC address table is for switch. This MAC address table is for switch 2. Is for switch 2. In this particular example, switch 1 is the root. Are we together? This interface has been blocked. So if host A wants to communicate to host B, they are going to communicate through switch 1 like that. Is that clear? But what happens if this link fails? What happens when that links fail? Okay, so let's try and see that. So this one has this. If I want to, this one, S2. If I want to send out a packet to host A, I send it out through this interface, which is correct. If I want to send a packet to a frame to host B, I send it out through G003, this one. Now, what you need to remember is that the aging time for MAC address entries is 300 seconds. Aging time for MAC address entries is 300 seconds. How many minutes are this? Is it 5? 5 minutes, eh? So you see what happens with STP. What happens with STP is this. If this link fails, what happens? It will activate what? Right? How many seconds does it take to change this to a root port? To change the alternate here to root port? Maximum of 50 seconds, right? Yeah, 50 seconds. But within 50 seconds, this entry and this entry will still be valid in the MAC address table. So what that means is even after the 50 seconds, after this one has been enabled, when a packet comes into this switch, it's still going to send it out through. If it's destined for host B, it's still going to send it out through 003, right? While we know that, oh, it won't reach because this link is down. What is the correct way? It's supposed to send it out through G002 because we have enabled this one. Are we together? Yeah, so that is the problem of MAC address table because of that aging time. Aging time is just too long. Just too long. 300 seconds. And therefore, if we send before the aging time expires, then our packet is going to be lost. Our frame is going to be lost. Okay. So what is the solution? Yes. Is something you don't understand? Yes. Okay. Okay. I asked what time will it take the alternate to transition to root port. So the total time for this transition is the maximum age expiration. Maximum age expiration plus what? Plus twice the forward delay. So the total here is going to be maximum age is 30 seconds, right? 20 plus 2 times 15. So that will give us 50 seconds. Is that clear? To root port. I understand what you're saying. Okay. So of course, okay, this question can be ambiguous. I totally agree with you. It can be ambiguous. Alternate to transition to root port, because unless now they've specified, for example, how long will it take for the alternate port to transition from blocking state to forwarding state. So these indeed will be clear. 30 seconds. Yes. You have a question? Uh-huh. Mm. Mm-hmm. Mm. Yes. 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 So in this particular case, it's an indirect link. Eh? Yes? Yes. This one is indirect. By the way, I don't know how they're using that indirect and direct, because when they talk of direct link, it means that the alternate is when they talk of direct link, it means that the alternate, let me just clear this and go back a little bit, just a little bit. Here. So when they talk of a direct link, it means that the alternate is what can I say? I'm lacking the word to describe this, but the alternate and the root, they're sharing the same BID. Are you getting the point? When they talk of indirect, it means the alternate is something like that. I don't know. So I've lacked the words to describe that, but I hope you get something there. Okay. So can we move on? Okay. So the solution to this incorrect MAC address entry is to use what we call the topology change BPDUs. Topology change BPDU. So the topology change BPDU will be sent immediately a topology change is detected on the network. So S3 detects that this link has gone down. So immediately it sends out a BPDU with the TCN set to 1. So it's going to send out a BPDU with the TCN field set to 1. So when switch 2 receives it, switch 2 is going to send what we call a topology change acknowledgement. A topology change acknowledgement. Are you seeing number 2 here? It's going to change a topology change acknowledgement. Acknowledging that, hey, switch 3, I have received your complaint. So don't send me any more TCNs. Don't send me more complaints. Are you getting the point? So that's what the acknowledgement is used for. Other than sending the acknowledgement, switch 2 is also going to send a TCN to the upstream switch. The upstream switch will send a TCA, then send a TCN to the other upstream switch until it gets to the what? Until it gets to the root. When the root receives the TCN, it's going to generate a BPDU with the TC bit set to 1. TC is topology. We have topology change and topology change acknowledgement. So TC is topology change BPDU. So it's going to set this flag to 1, the TC bit to 1. So it sends that. Now look what happens. It's going to send it to all the downstream switches. When any switch receives a BPDU with the TC bit set to 1, it's going to clear its MAC address table. It's going to empty its MAC address table and start learning MAC addresses afresh. Are you getting the point? Will that solve the preceding problem of wrong MAC address entries? Huh? See, that will happen faster than the 50 seconds. Right? Yeah, so every time all the downstream switches, any switch receives a BPDU from the upstream switch with the TC bit set to 1, you delete all your entries in your MAC address table and you begin learning MAC addresses afresh. So that is how we solve. That is how we solve this problem of incorrect MAC address table entries. So anyone with a question? Okay, so now let's look at basic TCP configuration. I'll move a little bit fast here. The command is easy. On system view, STP mod, then you specify the mod that you want to use. We have 3 STP mods: STP, RSTP, and MSTP. By default, the switch will work on which mod? MSTP. Then you configure the root bridge. You can use the command STP root primary to configure the root bridge. When you configure this command, then the switch priority is set to what? To 0, and it cannot be changed. Otherwise, for the other switches, you can use STP root secondary if you don't want them to be elected as the root bridge. They'll have a priority of 4096, which also cannot be changed. So you'll see that on the lab. You can also set the priority, change the priority of a switch by using the command STP priority, then the value. The value, as we said, is supposed to be in multiples of 40, 96, up to a maximum of this value, 32,768. Then to configure the cost of a port, that is the formula that you want to be used to calculate the cost. Then you can use the command STP path cost hyphen standard. Then you can choose one of the three. By default, Huawei uses the .1t, .1t, IEEE 802.1t standard. Otherwise, other than changing the formula for calculating the cost, you can manually specify the cost of the interface, so that STP will not calculate the cost using any of the standards. It will simply apply that cost. So STP cost, then a value. So you can give it 500, you can give it 10, etc., etc. Okay. Then we have the priority. We have the port priority. So to configure the port priority, you want it to be elected as the root port. So you go into the interface view, into that particular port, use the command STP priority, you give it a value. Maximum 128 in multiples of what? 16, right? Yes, multiples of 16. Otherwise, you can use the command STP enable to enable STP, RSTP, or MSTP on the switch. But this is normally enabled by default. It's normally enabled by default. When you did the data capture in the previous, lab, did you see STP packets on Wireshark? On the previous lab that you just did you see STP packets? You saw them, right? Yes, yet you didn't configure STP. So by default, STP is enabled on switches to prevent loops. Okay, so let's look at some basic STP configuration very fast here. So we want to deploy STP on 3 switches to eliminate loops on the network. So we want to configure switch 1 as the root bridge. We want to configure switch 1 as the root bridge, and we want to block G0022 on switch 3. So we want to block this one. So to do that, on switch number 1, we will choose the STP mod to be STP, configure it like that, enable STP, then set the priority to 0. If we set the priority to 0, we know that this guy will be elected as the root. On switch 2, we choose the mod. We need to choose the mod because by default, Huawei switches use MSTP. Are we together? Yeah, so that's why you need to change the mod to STP. Then we have STP enable to enable it. Then we set priority of 4096. On switch 3, STP mod, STP enable. So let's look at the next slide here. What do we do? So we can look at display STP brief. We can use the STP display STP brief command in order to have a view. This is on S3. Have a view of the interfaces and the role that they are playing. So we can see, for example, 21. We can see that Gigabit Ethernet 21 is in forwarding state, and the port role is root. 22 is the alternate. It has been blocked, so the state is discarding. Discarding is also known as blocking. So we didn't do anything. We didn't do anything to make 22 the alternate. We didn't configure anything because if you compare the PID of 21 and 22, you just know that 22 is the one that is going to be blocked from that particular topology. Okay, so let's look at the improvement of STP, which was done in a protocol called Rapid Spanning Tree, STP. So RSTP, let's begin by looking at the disadvantages. Disadvantages of STP. Disadvantages of STP. So, yes, it will ensure loop-free network, but it is slow to converge, leading to service quality deterioration. Also, if the network topology changes frequently, connection of the STP are frequently toned down, causing frequent service interruption. So that's the main problem of STP. Slow network convergence, and also topology changes really disrupt the network service. STP does not differentiate between port roles according to their states, making it difficult for less experienced admins to learn about and deploy this protocol. So ports in listening, learning, and blocking states are the same for users because none of these ports can forward service traffic. Also, in terms of port use and configuration, the essential differences between ports lie in the port roles, but not the port states. So we're going to see how RSTP really improves this. Then both root and designated ports can be in listening state or forwarding state. We've already seen that. So the port roles cannot be differentiated according to their states. So it also brings confusion somehow. Okay, then STP algorithm does not determine topology changes until the maximum age timer expires. Maximum age 20 seconds, delaying network convergence. STP requires the root bridge to send configuration BPDUs after the network topology becomes stable. In RSTP, you're going to see that every switch can be able to send configuration BPDUs, and not just the root switch. So the other devices process and spread the configuration BPDU through the entire network. So this also delays the convergence. As we said in STP, the configuration BPDUs will be sent from upstream switch. A switch receives it, takes about 1 second to change what is supposed to change before forwarding it to the downstream switch. So you see, that also takes time, especially if we have many switches. Okay, so then let's look at the improvements, or let's look at the overview of RSTP. RSTP was defined in IEEE 802.1 standard. It's an enhancement of STP, optimizes STP in many aspects. For example, it provides faster convergence, but it is also compatible with STP. When we say it's compatible with STP, it means if you have switches that you've configured, with RSTP, and you add another switch to that network, and that switch has been enabled with STP, then all the other switches will revert back to STP. Are you getting the point? So what we call backward compatibility. You've configured 5 switches on your network with RSTP. You bring in a new switch, does not understand RSTP because you've enabled STP. So all the other 5 switches are going to revert back to STP. So they are compatible. So STP introduces new port roles. We are going to look at them. When the root port fails, also the switch can enable the alternate port to obtain an alternate path from the designated to root bridge. RSTP defines 3 states of ports, as we are going to see, based on whether the port forwards user traffic or learns MAC addresses. In addition, it introduces a new port called an edge port. This port connects switches to end devices, to terminals. and this port enters in the forwarding state immediately after initialization. So it does not go through learning, listening, learning, then forwarding. No forward delay timer. You initialize an edge port, starts forwarding data immediately. So that is how RSTP is able to improve the working efficiency of STP. So improvements of RSTP. RSTP process configuration BPDUs differently from STP. So when the topology becomes stable, the mode of sending configuration BPDUs is optimized because every device is able to send BPDUs to downstream devices. So we don't wait for the BPDU from the root. We just alert the downstream. Then RSTP uses shorter timeout intervals of BPDUs. It also optimizes the method of processing inferior BPDUs. So if you want to understand how, you can check the topic, HCIP topic on RSTP. Otherwise, here we're just mentioning. We're not going very deep to RSTP. So RSTP changes the configuration BPDU format, and it uses the flag field to describe the port roles. STP was only using the two leftmost bits and rightmost bits. But now, RSTP utilizes all the flags to describe the port roles so that we can know the role that, the state that a port is in at any given point and the role it plays. RSTP topology change processing compared with STP, RSTP is optimized to accelerate the response to topology changes. So we're also going to see how. Okay, so RSTP port roles in RSTP. In RSTP, we have 5 port roles. So the first one is called root port. Number 2, we have the alternate. Then we have the designated port. Then we have backup port. Then you have edge. In summary, root port is the same root port as STP. Alternate port is the same as STP. So this one, as we identified earlier, the alternate port is the backup to the root port. Designated port, same as STP. Then it introduces what we call a backup port. The backup port is the backup to designated port. Backup to designated. Designated. Backup to designated. This one, backup to root port. Edge port connects terminals and devices. RSTP, unlike STP that had 5 port states, this one has 3. Discarding, this one has 3. Discarding, the other one is learning and forwarding. Okay. Okay, so let's look at this example. So we have the root bridge. As we said, all ports will be designated on the root. Ports that are closest to the root, determined by the shortest RPC or smallest RPC, will be root ports. Then we can have designated and we block one, like we've done there. So alternate is still alternate. So here, in case we have two links, connected to this bus, we've blocked this one. So we need to choose between these two, one to be designated and one to be backup. So again, we compare the PID. We compare the PID to choose between designated and backup here. So that if this designated goes down, then this guy becomes the new designated port. So that's why we say that the backup port is the backup of the designated port, while the alternate port is the backup of the root port. Then we have the edge port. So as we've said, edge port is used to interconnect end devices. Edge ports can transition. The power of the edge port is this: transition from the disabled state to forwarding state immediately. So no forward delay, unlike in STP. No forward delay. What you need to know, characteristics. It does not receive or process configuration BPDUs. Also, edge ports do not participate in RSTP calculation. So it's not used to create the tree, the loop-free tree. No, edge ports, no. As we've said, it can transition from disabled to forwarding without delay. Lastly, edge ports become common STP port once it receives a configuration BPDU. Anytime an edge port receives a configuration BPDU, it becomes a common STP port, meaning it's going to trigger network convergence. It's going to trigger an election, an STP election. So if this is a hacker and they send a configuration BPDU to this edge port, then it's going to cause network flapping, because your network is going to waste about 50 seconds to recalculate the STP loop-free tree topology. So there are ways in which you can configure that to prevent hackers from causing your network to flap. There's a security feature that you can use for that. So when you get time, you can research about it. So port states in RSTP deletes two port states that were defined in STP. reducing the port state to just 3. So we have forwarding, we have learning, and all the rest that were in in STP, listening, blocking, and disabled. All of them are referred to as discarding. Only root ports and designated ports can be on forwarding state, just like in STP. Only root port and designated port can be on learning state, just like on STP. Otherwise, all the other ports can be on discarding state. And of course, we know, we've already gone through this, that if a port does not forward user traffic or LAN MAC addresses, then that is discarding. If it can not forward but can LAN MAC address, which state is that? On the other hand, if it forwards and LANs, forwarding state. Very good. Okay, we are about to end. So STP advancements. Now, another problem with both STP and RSTP is that when we create multiple VLANs, all the VLANs share the same spanning tree. So all of them have one spanning tree. What's the problem with that? What's the problem with sharing the same tree? So this is a switch. In this switch, we have VLAN 2, VLAN 3, VLAN 4, blah, blah, blah. But we've also created STP to run between these aggregated switches and this access switch. So STP has blocked G002, right? So G002 cannot forward data. So data from all VLANs have to go to the core via switch 1. So are you seeing a problem with that? Two problems. Number one, we are wasting link bandwidth because we are not utilizing this particular bandwidth. Number two, we are overloading switch number 1. We are overloading it. So those are the two main problems. Two main problems that we are having there because of using the same tree. So the solution to that is what we call, I'm meeting this for the first time, this VBST, but maybe I can start from MSTP before I go to VBST. So MSTP, let's try and understand what MSTP is. MSTP, IEEE released it. It's called the 802.1s standard. Defines multiple spanning tree protocol. So in 2002. So even as the name suggests, then instead of having one tree, we can have multiple spanning trees. Then VLANs can share those spanning trees. So MSTP is also compatible, that is backward compatible with STP and RSTP, can rapidly converge, provides multiple paths to load balance VLAN traffic. So how does it work? Let me see. I know these diagrams are a little bit okay, I'm unable to do that. Okay, so how it works is this. How it works is this. MSTP, it maps VLANs to what we call multiple spanning tree instances, MSTI. So each spanning tree has what you call an MSTI ID, multiple spanning tree instance. So for example, you're having MSTI1, MSTI2. So spanning tree from MSTI1, spanning tree for MSTI2. So multiple VLANs can share one spanning tree. For example, one of the commonly used methods of doing it is this. Even numbered VLANs are mapped to MSTI1. Then odd numbered VLANs are mapped to MSTI2. So only two spanning trees are maintained on the network. So in this particular case, in this particular example, on MSTI1, switch 1 is the root. Sorry, switch 1 is the what? For the first spanning tree, switch 1 is the root. And what do? We block this interface. Are we together? On the other hand, for this other tree, MSTI2, we make switch 2 the root. And we block what? This one. Then we say, if data is coming from VLAN, VLAN 1, 3, or all the odd numbered VLANs, then we want it to pass through MSTI1. Otherwise, for the even ones, we want them to pass through MSTI, because I don't know whether you're understanding what I'm saying. This is what we are saying. We have two spanning trees, and depending on the VLAN from which you're coming from, we are going to either open or block a certain port. So that's what we are saying. So if you're on VLAN 2, we've blocked this port for you. And we've opened this one. If you're on VLAN 1, 3, blah, 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 odd numbered VLAN, we've blocked this one. We've opened this one. Are you getting the point? Yeah, so that's how the multiple spanning tree works. Okay, so here they're just mentioning it just as a summary. If you want to learn further about MSTP, you can also check my HCIP videos. I teach it there. So I'm meeting this for the first time. It's called VLAN-based spanning tree, VBST. It's a Huawei standard. So Huawei provides VBST. It constructs a spanning tree in each VLAN. So that traffic from different VLANs load balance along different spanning trees. So it's almost similar to MSTP. Only difference being it can create a tree for each VLAN, right? But really it's almost the same thing. So it can create VLAN. For VLAN 1, it creates that tree. So for VLAN 1, switch 1 is the root. For VLAN 2, switch 2 is the root. For VLAN 3, this one is the root, but we've blocked. So you see, look here. For VLAN 1, from this figure here, for VLAN 1, which port have we blocked? We've blocked this one, right? To have this tree. For VLAN 2, which port have we blocked? Let me undo. For VLAN 2, which port have we blocked? We've blocked this one, right? Then for VLAN 3, which port have we blocked? This one. So that is what they are calling a VLAN-based spanning tree. So I see that it's almost similar to MSTP. Okay, so just a brief about MSTP. It divides a switching network into multiple regions, what we call MSTP regions, each of which has multiple spanning trees that are independent of each other. So each spanning tree is called a multiple tree instance, MSTI. MSTI corresponds to a set of VLANs. So you can add multiple VLANs on a single MSTI. So binding multiple VLANs to a single MSTI, it reduces and also improves network resource usage like the CPU, because you're going to do load balancing. Data from certain VLANs will go through switch 1. Others will go through switch 2. So load balancing. So the topology of each MSTI is calculated independently and traffic can be balanced among MSTIs. So multiple VLANs with the same topology can be mapped to a single MSTI. Forwarding set of the VLANs for an interface is determined by the interface state in the MSTI. So please learn more about MSTP when you get time from my HCIP videos. The other important concept is the concept of stack and tree networking of campus networks. Okay. So here we have a technology. We have a technology called the iStack. Just a moment. iStack. iStack here stands for intelligent stack. Now, this is one of the features you need to look for when you're going to buy a switch, so that you can be able to know whether it supports this capability. So iStack technology enables you to bind several physical switches into a single logical switch. Are we together? Enables you to bind several physical switches into a single physical switch. Are you seeing that if we do this, we are not even going to need STP, because we are not going to have a loop? Are you seeing that? If we shift from this, if we shift from this traditional architecture to iStack. So first of all, we begin by binding the physical switches, aggregation switches, right? Then we also go ahead and bind. So instead of blocking interfaces, we bind these interfaces so that they can work as single logical links. So we're going to do a topic on link aggregation. So link aggregation is the name that is given to that particular exercise of combining several physical interfaces into a single logical interface. So if you do this, advantages: simplifies network management, because you don't need to worry about loops, you don't need to worry about STP, MSTP, or RSTP. You also improve network reliability, because when you combine these two switches, you are combining their power. When you combine two links, for example, if they are 1 gig, you combine two, they become 2 gig. Are we together? Yeah, so you improve network performance and also network reliability. So that is what we call the intelligent stack technology, where you can be able to combine devices or links to single logical links. So that's the other solution, iStack. iStack is a solution to loops, layer 2 loops. Are we together? Other than STP, RSTP, MSTP, iStack, solution to loops. The other solution to loops is what we call smart links. Smart links. Smart links. Okay, so we can see smart link is tailored for dual uplink networking. Uplink. So S3 is connected to the aggregation layer switches via these two uplinks. So if we have these two uplinks, then we have the probability of having a loop. having a loop. So when we are using Smart Link, then this can be able to eliminate layer 2 loops. So what happens when the network is normal? Only one of the two links is active. The other link is in standby state, does not carry service traffic. So we have the two, but only this port is working. This one disabled, acting as a backup. So when active link is faulty, traffic is switched to the standby link in milliseconds to ensure proper data forwarding. So Smart Link is easy to configure in order to deal with loops compared, for example, to STP. Otherwise, Smart Links do not involve protocol exchange. It does not have any packets like STP has BPDU and also RSTP and MSTP. Therefore, it greatly improves speed and reliability of the network. So normally you create a Smart Link group. So when you add those interfaces into the same Smart Link group, then one becomes active, the other one is on standby mode. If this one goes down, this one is activated immediately in seconds. Okay, so ladies and gentlemen, take time to discuss this question here. Maybe just something I would love to mention is this one, that STP cannot meet requirements of modern campus networks. So you're not going to be configuring STP on your networks as network engineers. However, understanding the working mechanisms of STP helps you better understand the working mechanism and deployment of RSTP and MSTP. Because both of them are just improvements of STP. So that's why you need to understand how STP works. But on your networks, you'll either be configuring RSTP or MSTP. Most probably MSTP. To learn how to configure MSTP, please watch my HCIP videos after you're done with this certification. Thank you very much. Asanteni sana for